For example, the Earth's axial tilt, the angle of Earth's axis to the ecliptic have very precise numbers. The universe is full of such specific values. Can you inform us about the fine-tuning in the universe?
Yeah, when it comes to fine-tuning, there is sort of two levels of fine-tuning we want to make a distinction about. The first level of fine-tuning is we can ask the question, why do the laws of physics have to have the constants that they have? For example, the speed of light is 300 million, 3 times 10 to the 8 meters per second. So we can ask the question, okay, it had to be some value. Maybe it would have been 2, it could have been 2 times 10 to the 8 meters per second. Maybe it could have been 4. And is it, we just happen to have 3. Is that maybe not very special? It turns out it is special. It turns out you cannot deviate from 3 times 10 to the 8 meters per second very far before the conditions for life in the universe are not favorable. That is one example. The gravitational constant is another one. If the gravitational constant is too strong or too weak, it has very big effect on the formation of planets. There are forces inside the nucleus. That's the strong nuclear force and the weak nuclear force. Those forces, those parameters are also fine-tuned. The sun is powered by a nuclear process where hydrogen and helium and beryllium and carbon and oxygen are formed in a series of nuclear interactions. It turns out that these energy levels are well connected, well matched to each other to make this happen. If they were just a little bit different, there would be no production of oxygen, for example, or very little production of oxygen. And so what we find is that the universe is very fine-tuned in terms of the constants of nature, those things that are expected to be the same all over the universe, but the value itself is a very special value. And the value is conducive to life in the universe. So that's the fine-tuning of the parameters of the universe. But even in a universe that is so spectacularly fine-tuned, as ours seems to be, extremely fine-tuned, even when you have this kind of a universe, you can ask the question, how easy is it, how expected is it to have a planet like the Earth in this kind of universe? Then you might be talking about, well, what are the processes that produce a planet? There is a protoplanetary disk, there is a aggregation of materials, there is the formation of the planet, there is the bombardment that occurs because of the material in the universe, in the protoplanetary disk. Then there is the stellar formation that is going on. What kind of star are you forming? And it turns out that those conditions are also rare. In other words, even if you have a very friendly universe like ours, exceedingly well-designed universe as ours, even then, when you ask the question, the laws that are operating in this universe, would they easily produce many, many Earths? Like if we go to the next star, are we going to find another Earth? Well, we have a very good understanding now of what are the conditions and what does it mean when we say an Earth. First, we want a terrestrial planet, for example. In our own solar system, the Earth is a terrestrial planet, meaning it has it's rocky. It has water, but it has rocks. But if I go to Jupiter, it's not that kind of a planet. If I go, if you arrive at Jupiter, it is just a gas, and the pressure builds up very rapidly as you descend into the gas, completely unfriendly to life. So you need a terrestrial planet, you need water, but you don't want too much water because you have to have those interfaces between land and water where the water thickness is small enough that there is a combination of moisture and there is a combination, and sunlight that penetrates the water to keep the warm waters. That much of the food production in the sea occurs in the places where water is touching the land. When you go really deep, there's not enough sunlight in the deep to produce abundant life, essentially. And then you can ask, what does it take to have a climate that is stable? And the Earth's axial tilt gives us the seasons, but it also is an axial tilt that is not doing this as we go around. This is not the case for our planetary neighbors. Mars, for example, does not have a stable axial tilt. Where does this axial tilt stability come from? We have this very large moon relative to the Earth. Our moon is actually part of the Earth-Moon system, is actually part of a system that is really designed to keep us having a stable climate. So the moon is doing multiple things for us. It's not just there randomly. It has a job. We can talk about Jupiter. Jupiter has a job relative to the Earth, and the job is that Jupiter's mass is so high that it absorbs to itself. Its gravitational attraction essentially sweeps up and cleans up the debris in the inner solar system. For example, I was much younger, maybe 20 years ago, there was a comet that was viewable in the sky, the Shoemaker-Levy comet, and everybody was excited. It was in the news, and people would get out their telescopes and watch this comet. Well, eventually, what happened to this comet? It crashed into Jupiter. And that's what Jupiter does. We're thankful to Jupiter because things crash into it. Asteroids and near-Earth objects that could potentially, and sometimes do, collide with the Earth. The fact that they don't do that much more often is because of a massive gas giant, which Jupiter is, at a 5 astronomical unit orbit with very small eccentricity. And what I mean by eccentricity is that the orbit of Jupiter is almost a perfect circle. If Jupiter had a high eccentricity orbit, it would be an elliptical orbit. What does that mean? That means that here is the orbit of the Earth. Now, orbit of Jupiter, if it comes in and out, over a very long period of time, over millions of years, it can collide with the Earth and send us out of the solar system. This never happens because Jupiter's orbit is so well behaved. So high mass gas giant at a large, low eccentricity orbit is what we have with Jupiter, which is perfectly made for our convenience. And so it is, there's this principle that is supposed to be there, that of what's called the principle of mediocrity, that says that we are nothing special. We shouldn't have this high view of ourselves. But what we find is, in reality, that things are extremely well matched to our health. Our planet is well protected. We have the moon doing what it's doing. We have the Earth. The Earth has a magnetosphere. The magnetosphere is protecting us from the solar activity. So the list is a very long list. And so there is, one could go a very long time talking about all the things that are true in this case, about the Earth's survivability.